Next problem is show that 5 raised to 103 and plus 103 raised to 53 is divisible by 39. So we treat this 53 raised to 103 first. So 53 is congruent to minus 1 module 3, because what is 53 minus 1? That is 53 plus 1, and 53 plus 1 is 54, and 3 divides to 54. 3 divides to 54. Okay, and therefore we find this minus 1 by trial and error method. So we take this 53 at this place and is congruent to minus 1. So by using trial and error we find this minus 1, and this 103 is congruent to what? Module 3. That is, when 3 divides to 103 is true, that 3 divides to 103. No, 3 does not divides to 103, but 3 divides to 103 minus 1. So take there, here is at place this 1, and then 53 raised to take the 103 power of both sides. So minus 1 raised to 103. Next step, minus 1 raised to odd power is minus 1, and here is also take 53 power of both sides. 1 raised to 53 is 1. And then by using the theorem that A is congruent to B module N and C is congruent to D module N, then A plus C is congruent to B plus D. That is, this plus this is congruent to minus 1 plus 1 module 3, that is 0. And therefore 3 divides to 53 raised to 103 plus 103 raised to 53, because we have at this place remainder is 0. That is, if we divide, what we have from this, by using the definition of congruence relation. What is the definition of congruence relation? A is congruent to B module N if and only if N divides to A minus B. So what we have from this equation, that 3 divides to this minus 0, that is 3 divides to this number. Okay, so we have this answer that is divisible by, we have to prove this divisible by 39. We have here 3 divides to this. Okay, and then 53 is congruent to 1 module 13. 53 is congruent to 1 module 13, because 13 into 3, this 3 is what? Is 39. So we take 13 this number at this place, because 3 into 13 is 39. So 53 is congruent to 1 module 13, because 13 divided to 53 minus 1, that is 52. And then 103 raised to 53 is congruent to minus 1 module 13. 103 raised to 53 is congruent to minus 1 module 13. So first take 103. 103 is congruent to minus 1 module 13. And then take 53 power. Don't write here 53 first. Write 103. Here write 103 is congruent to minus 1, because 103 minus 1, that is plus 1. 103 plus 1 is 104, and 13 divides to 104. So and then take 103 power of both sides here, and here take 103 raised to 53. Don't write here 150 raised to 53, and minus 1 raised to 53 module 13. And then 1 raised to 103 is 1, and minus 1 raised to 53 odd power is minus 1. And then add these two. This is A congruent to B and C congruent to D. Then A plus C is congruent to D plus C plus D. And then here we have 0. And then 13 divides to this number. So 3 divides to this number, 13 divides to this number, and therefore, and the greatest common divisor of 3 and 13 is 1, and therefore 3 into 13 divides to this number, that 53 raised to 103 plus 10 raised to 53, and therefore this is number is divisible by 39. So all these examples, these previous examples, are same type. So we start with some equation. Divide by 7 means take module 7. Here is the model divisible by 39. 39 is very large number. That's why take first 3 and then 13. 39 3 multiplication is 39. So next example is next theorem is important. What is the theorem? First we see what is the inverse of the residue class. So like in Zn, Zn, we know that this Zn means what? The set of residue classes of module n. So for I bar belongs to Zn, it is not always possible to find J bar in Zn such that I bar into J bar is equal to 1 bar. For instance, if we take in Z7, if you take 3 bar, then we have 5 bar in Z7 such that 3 bar into 5 bar is what? 3 bar into 5 bar is 15 bar. And in Z7, 15 bar is what? If we divide 15 by 7, then 2 is the question. That is 2, 7 are 15 and 14 and plus 1. 1 is the remainder. So 3 bar into 5 bar is what? 1 bar. And that's why in this way, we can find for I bar in Zn, J bar in Zn such that I bar into J bar is equal to 1 bar. But this is not always possible to find such a pairs for every element of this Zn. So in fact, from the table, we see that to each I bar not equal to 0 bar in Zn, there exists J bar in Zn, Z7 such that I bar into J bar is equal to 1 bar. So if we observe this table, then 1 bar into 1 bar is 1 bar. So this is the pair that 1 bar into 1 bar is 1 bar. Then what is 2 bar into 4 bar is 1 bar. So 2 bar and 4 bar, their multiplication is 1 bar. So what is 3 bar and 5 bar is 1 bar. 3 bar and 5 bar is 1 bar. And 4 bar and 2 bar is 1 bar. 5 bar and 3 bar is 1 bar. 6 bar into 6 bar is 1 bar. And so here is the sentence that we see that for each I bar in Zn not equal to 0, there exists J bar in Z7 such that I bar into J bar is 1 bar. So what are that such a pairs? List such a pairs. So what are the pairs? So 3 bar and 4 bar, this 3 bar and 5 bar. Then what are the pairs, other pairs? 5 bar and, so such pairs are what? If you observe this, 1 bar, 1 bar, then 2 bar and 4 bar. So 3 bar and 5 bar. So these are the pairs, 6 bar and 6 bar. 6 bar into 6 bar is 1 bar. So in Z6, but what happened in Z6? For 3 bar and 4 bar, we cannot find such a J bar in Z6. We cannot find 3 bar into any element of Z6 is equal to 1 bar. So when these pairs exist, and if I bar into J bar is 1 bar, then I bar and J bar are called inverses of each other or multiplicative inverses of each other. So what is the definition of multiplicative inverse? This is the definition of multiplicative inverse. If I bar into J bar is 1 bar, then inverse of I bar is J bar and vice versa. That is inverse of J bar is I bar and inverse of I bar is J bar. And what is the notation for to denote the inverse? So I bar inverse is denoted by this notation, right? I bar raised to minus 1 is equal to J bar. Means multiplicative inverse of I bar is J bar and multiplicative inverse of J bar is I bar. Okay, that is if when I bar into J bar is 1 bar, then we say I bar and J bar are inverses of each other or multiplicative inverses of each other. So here is the example, find all pairs I bar and J bar in Z8 such that I bar into J bar is 1 bar. So if you find such a pairs in Z7, then what is the pairs? So if you observe the table in Z6, so the pairs are 1 bar and 1 bar. 1 bar, that is inverse of 1 bar is itself 1 bar. Then inverse of 2 bar is what? 4 bar. 2 bar into 4 bar is 1 bar. And inverse of 2 bar is 4 bar. Therefore, inverse of 4 bar is also 2 bar. Then inverse of 3 bar is what? Inverse of 3 bar into 5 bar is 1 bar. So 3 bar, inverse of 3 bar is what? 5 bar. And therefore, inverse of 5 bar is also 3 bar. Okay. And then inverse of 6 bar is itself 6 bar because 6 bar into 6 bar is 1. So here is the problem that finds 7 bar inverse. So 7 bar inverse is 7 bar. Why? Because 7 bar into 7 bar is 49 bar. 49 bar and 49 bar in Z12 is what? If you divide 49 by 12, then what is the question? 12 for the 48, and plus 1 is the remainder. So 7 bar into 7 bar is 1 bar. That's why 7 bar inverse is 7 bar here in Z12. Like this, in Z7, what is 3 bar inverse? Is 3 bar inverse is what? Is 5 bar. Like that. Because 3 bar into 5 bar is 1 bar. So if I bar into J bar is 1 bar, then I bar and J bar are called inverses of each other. Here is the example. So find inverses of each element if exist of Z8. The inverse of every element of Z8 does not exist. Some inverses of some elements of Zn are exist. So find all pairs or find inverses of each element of Z8, or find all pairs I bar and J bar in Z8 such that I bar into J bar is 1 bar. The questions meaning of the question, the two questions are same. That is, find inverses of each element if exist. So Z8 contains these 8 elements, 0 bar to 7 bar. This is the Z8, the set of residue classes module 8. And then we have to find I bar and J bar such that I bar into J bar is 1 bar. And here is the theorem that if and only when the greatest common divisor of I bar and J bar, when the greatest common, when the inverse of I bar exists in Zn, if the greatest common divisor of I and N is 1. And so otherwise you find by using these pairs, or by using drawing the table. And so here is what, if the same question is for Z6, 7, then use the table. So here is N is 8, and the greatest common divisor of 1 and 8 is 1. Therefore, the inverse of 1 exists. Then in greatest common divisor of 2 and 8 is not 1. The greatest common divisor of 3 and 8 is 1. Therefore, the inverse of 3 exists. Then 3 bar exists. 4 and greatest common divisor of 4 and 8 is not 1. 5 and 8 is 1, and therefore the greatest inverse of 5 bar exists. And then greatest common divisor of 6 and 8 is not 1, but 7 and 8 is 1. So for I bar we have 1 bar into 1 bar is 1 bar. So what is the inverse of 1 in Z8 is itself 1 bar. Then if we take 3 bar, then 3 bar into 3 bar is 9 bar. And 9 bar is 1 bar in Z8. So inverse of 3 bar is itself 3 bar. Inverse of 1 exists, inverse of 3 exists, inverse of 5 exists. So what is the inverse of 5 bar? 5 bar into 5 bar is 25 bar and is 1 bar. Therefore, inverse of 5 bar is itself 5 bar. And inverse of 7 bar is what? 7 bar into 7 bar is 49 bar, and then that is equal to 1 bar. In Z8, that is, if you divide 49 by 8, then 1 is the remainder. And so 1, 3, 5, 7 are the pairs with themselves. That is the pair such that I bar into J bar is 1 bar. Okay. So that is 1 bar, 1 bar, 3 bar, 3 bar, 5 bar, 5 bar, and 7 bar, 7 bar are the pairs such that I bar into J bar is 1 bar. So either draw the table or use the theorem. What is the theorem? That the inverse of I bar exists in Zn if the greatest common divisor of I and N is 1. So that is the previous theorem. So if the same question, that is, find the inverse of all elements of Z7 if exist, if this is the question, then what is the answer? Draw this table. Draw the only multiplication table, right? For Z7, we have to find the inverses. So inverse of 1 exists in Z7 because the greatest common divisor of 1 and 7 is 1. Inverse of 2 bar also exists because 2 and 7 greatest common divisor is 1. 3 and 7 greatest common divisor is 1. 4 and 7 greatest common divisor is 1. 5 and 7 greatest common divisor is 1. And 6 and 7 greatest common divisor is 1. Only the greatest common divisor of 7 and 0 is what? 7. And then for 0, inverse of 0 bar does not exist. So what is the inverse of 1 bar? 1 bar inverse is itself 1 bar. 2 bar inverse is 4 bar. 3 bar inverse is 5 bar. 4 bar inverse is 2 bar. 5 bar inverse is 3 bar. 3 bar inverse is 5 bar means 5 bar inverse is 3 bar. In this way, 6 bar inverse is 6 bar. Because 6 bar into 6 bar is 1 bar. So use the theorem or to find the inverse of each element, either use this theorem or draw the table for multiplication in Z8 and then find inverses of each element. So here is the question. Write the composition table for addition and multiplication in Z6. So this is the table for addition in Z6. This is the table for multiplication in Z6. Okay, and then we have to find the additive inverse. So what is the additive inverse of the each element in Z6? So what is the definition? Here is the definition. If a bar plus b bar is 0 bar, then a bar and b bar are called, then additive inverse of a bar is what? B bar, and vice versa. That is additive inverse of b bar is a bar. And we denote the additive inverse of a bar by this notation, minus a bar. So first we see the multiplicative inverse, the question answer of this question number 3. So if you observe the table, multiplication table, and if you observe the second this row, then there is no one in this row. There is one at this place. So 1 bar into 1 bar is 1 bar, and therefore inverse of 1 bar is 1 bar. Inverse of element and its inverse is noted here. So 1 bar inverse is 1 bar. Then 2 bar into what is equal to 1 bar? So in the row of 2 bar there is no 1. There is no 1 bar, and therefore inverse of 2 bar does not exist. Inverse of 2 bar does not exist. What is the, if you observe the row of 3 bar, then there is no one at this any place, 1 bar. There is no 1 bar in any place, and therefore 3 bar inverse does not exist. If you observe 4 bar table or row, then there is no one. If you observe 5 bar, then this 5 bar into 5 bar is 25 bar. Here write 1 bar, don't write here 2 bar. It is the mistake, write 1 bar. So 5 bar into 5 bar is 25 bar, and if you divide 25 by 6, because we are in Z6, so if you divide 25 by 6, then 1 bar is the remainder. So 5 bar inverse is itself 5 bar. So only 2 elements of this Z6 has multiplicative inverses. Only 2 elements in Z6 has multiplicative inverses. While in Z7, 6 elements has the multiplicative inverses. In Z8, 4 elements has the multiplicative inverse. So when the multiplicative inverse exists, why the multiplicative inverse of 0 bar does not exist? Because 0 bar and 6 bar, its greatest common divisor is not 1. Then 1 and 6 greatest common divisor is 1, and therefore 1 bar inverse exists. The greatest common divisor of 2 and 6 is 2, not 1, and therefore 2 bar greatest common divisor, the inverse of 2 bar does not exist. Similarly, 3 and 6 greatest common divisor is not 1, is 3, and therefore the inverse of 3 bar does not exist. Similarly, 4 and 6 greatest common divisor is what? 2. 4 and 6 greatest common divisor is 2, not equal to 1, and therefore 4 bar greatest common, therefore 4 bar inverse, multiplicative inverse does not exist. Similarly, 5 bar and 6, 5 and 6 greatest common divisor is 1, and therefore inverse of 5 bar exists. So, and what is the additive inverse? If this is the definition, their addition is 0 bar. So 0 bar plus 0 bar is 0 bar, and therefore additive inverse of 0 bar is itself 0 bar. Then 1 bar plus 5 bar is 0 bar, and therefore 1 bar additive inverse is 5 bar. So how we can denote one additive inverse of 1 bar is 5 bar, and the additive inverse of 1 bar is 5 bar, and therefore additive inverse of 5 bar is 1 bar. Vice versa. That is, if a bar plus b bar is 0 bar, then a bar and b bar are additive inverses of each other. And how we can denote additive inverse of 1 bar is 5 bar? Write this notation, minus 1 bar is equal to 5 bar. Right? Minus 1 bar is equal to 5 bar. Then 2 bar plus what is equal to 0 bar? 2 bar plus 4 bar is 0. And therefore 2 bar additive inverse is 4 bar. How we can denote this? Write minus sign, then 2 bar is equal to 4 bar. That is, minus 2 bar is 4 bar. And obviously minus 4 bar is 2 bar. Then 3 bar plus what is equal to 0 bar? 3 bar plus 3 bar is 0 bar. So 3 bar additive inverse of 3 bar is 3 bar. Additive inverse of 4 bar is 2 bar. Additive inverse of 5 bar is 1 bar. So these are the definition of additive inverse and multiplicative inverse. The multiplicative inverse is also called just inverse of the element. Inverse of the element means multiplicative inverse, and the additive inverse means the additive inverse. Okay, but multiplicative inverse The another word is what? Just inverse. Find inverse of each element means find multiplicative inverse of each element. So when the multiplicative additive inverse of each element exists, but multiplicative inverse of each element of Zn does not exist. When the multiplicative inverse exists, so this is the theorem for the multiplicative inverse exists for I bar in Zn, there exists J bar in Zn such that I bar into J bar is 1 bar, means the J bar becomes a inverse of I bar. When I bar into J bar is 1 bar means what? The inverse of I bar is equal to J bar if and only if the greatest common divisor of this I and N is 1. So if you observe in Z8, so 0 and 8 greatest common divisor is 8. 1 and 8 greatest common divisor is 1, and therefore inverse of 1 bar exists. The greatest common divisor of 2 and 8 is 2, not equal to 1. And so 2 bar multiplicative inverse of 2 bar does not exist in Z8. 3 and 8 greatest common divisor is 1, and therefore inverse of 3 bar exists. Then 4 and 8 greatest common divisor is 4, and that is not equal to 1, and therefore 4 bar inverse does not exist. Similarly 5 and 8 greatest common divisor is 1, and therefore 5 bar inverse exists. And in this way 6 and 8 greatest common divisor is 2, not equal to 1, and therefore 6 bar inverse does not exist. And the 7 and 8 greatest common divisor is 1, and therefore 7 bar inverse exist. Okay, so in this Z8 only these 4 elements 1, 3, 5 and 7, for these 4 elements inverse multiplicative inverse exist. And what are that? 1 bar inverse is itself 1 bar, 3 bar inverse is 3 bar, and all these things. So first, when the inverse of I bar in Zn exists, if the greatest common divisor of I and N is 1. So this is the theorem. For I bar in Zn, there exists J bar in Zn with I bar into J bar is 1 bar, means J bar is inverse of I bar, or I bar inverse is equal to J bar if and only if greatest common divisor of I and N is 1. So same theorem in another form. This is the for element A bar in Zn has an inverse for multiplication module N, that is the if when A bar has multiplicative inverse if and only if the greatest common divisor of A and N is 1. So the wording of these two theorems are different, but the meaning is same. That is this theorem 13 and the theorem 3.8, both are the meaning are the same. The notations are different. So here is the notation I bar, and there exists J bar in Zn such that I bar into J bar is equal to 1 bar, means what? The multiplicative inverse of I bar exists in Zn if and only if the greatest common divisor of, here is the notation A, in place of A in this theorem the notation is I. Okay, the greatest common divisor of I and N is 1. So the theorem is of type if and only if. So proof is in the two parts. The first part, assume that the inverse of I bar exists and suppose it is J bar, and then prove the greatest common divisor of I and N is 1. That is the theorem of the type if and only if. So when the if and only if type theorem prove, the proof of the if and only if type theorem is in the two parts. Here is the if and only if type. When P implies P if and only if Q is logically equivalent to P implies Q and Q implies P. Okay, so first show assume P, prove Q. This is the first part, and then second part is what? Assume Q and prove P. The first part is called necessary part, and the second part is called sufficient part. So the proof is in the two parts. The proof of the theorems of the type if and only is in two parts. So assume P, prove Q, and assume Q. In second part, assume Q and prove P. So here is what is assumption. Suppose for I bar in Zn, there exists J bar in Zn such that I bar into J bar is 1 bar. This is our assumption. And what do I have to show? Greatest common divisor of I and N is 1. We have to show greatest common divisor of I and N is 1. This is the part 1. So what is our assumption? I bar into J bar is 1 bar, or the inverse of I bar exists. Here is also sentence that inverse of A bar exists in Zn, means suppose the inverse of A bar is B bar, and then A bar into B bar is 1 bar. Okay, so right here the notation into suffix N, means multiplication modulo n, or write dot on it. Okay, so here is the notations I bar and j bar, and here is the notation a bar and b bar. It's only change in these two theorems. So suppose the inverse of I bar exists, means suppose the j bar is its inverse, and then I bar into j bar is 1 bar, and I bar into j bar is I into j bar by using definition of multiplication. And then these two residue classes or equivalence classes are same, means they are these elements I into j and 1 are related. And what is the relation? Here is the relation, congruence relation. So I into j is congruent to 1 modulo n. That is, if the equivalence classes are same, then the elements are related. So I into j is congruent to 1 modulo n. And this implies n divides to I into j minus 1. N divides to I into j minus 1. And therefore, n divides to I into j minus 1. This is by using definition of congruence relation. That is, a is congruent to b modulo n implies n divides to a minus b. And then by using definition of divisibility, n divides to this number means this number expressed in the form n into some integer. I into j minus 1 expressed as n into k for some k belongs to j by using definition of divisibility. And then I into j minus n into k, shift this n k in the left side and then minus 1 at the right side. And then write this I into j plus n into minus k, right? Absorb this minus sign at this place, is equal to 1. And this implies the greatest common divisor of I and n is 1. Because what is the theorem on the greatest common divisors? If d is the greatest common divisor of a and b, if and only d expressed in the form ma plus nb. That is, if d expressed in the form ma plus nb, then greatest common divisor of a and b is what? Is d. Like that. So by using that theorem or examples, this I into j plus n into minus k is equal to 1 means the greatest common divisor of I and n is 1. And that is we have to show that greatest common divisor of I and n is 1. Now in the second part, assume that the greatest common divisor of I and n is 1, and prove that for I bar there exists j bar, some j bar, that is the inverse of I bar exists. What we have to show in the second part, we assume that suppose that greatest common divisor of I and n is 1. And what we have to show? We have to show for I bar in Zn there exists some j bar in Zn such that I bar into j bar is 1 bar. Or what do we have to show? We have to show inverse of I bar exists in Zn. So assume that greatest common divisor of I and n is 1, and therefore by using that theorem, that if the greatest common divisor of a and b is d, then d expressed in the form am or ax plus by. Okay. So there exists some integers p and q, right? Either p and q or x and y or m and n. But already n is a notation in the theorem, so don't take m and n. Either take p and q or x and y in z such that 1 is equal to iq plus np. Or instead of p and q, use the notation x and y. And then taking bar of both sides, that is equivalence classes of both sides, residue classes of both sides, and then by using definition of addition, a plus b bar is a bar plus b bar, and then by using the definition of a into b bar is a bar into b bar, we have this. And in Zn, what is n bar? N bar is 0 bar. In Zn, n bar is 0 bar. So what is in Z6? If you observe Z6, so what is in Z7? What is 7 bar? 7 bar is 0 bar. In Z7, 7 bar is 0 bar. In 6 bar is 0 bar. Okay. In Z7, 7 bar is 0 bar. So like that. In Zn, in general, in Zn, n bar is what? N bar is 0 bar. And so right here, 0 bar into p bar is 0 bar. Therefore we have I bar into q bar is 1 bar. And that is, we have the element q bar such that I bar into q bar is 1 bar. That is, q bar becomes inverse of I bar. And hence theorem. That is what we have to show. For I bar in Z bar, there exists j bar. J bar means, this is the notation. That is, we have to show any element in Zn. We have to find the any element in Zn such that I bar into that element is 1 bar and that element is q bar. So I bar into q bar is 1 bar, and this prove the theorem, complete the proof of the theorem. This theorem is same theorem that a bar inverse exists. In first part, we assume that a bar inverse exists, And suppose b bar is its inverse, then a bar into b bar is 1 bar, and then a b bar is equal to 1 bar. Then these two elements are, these residue classes are same, means these two elements are related. And then n divides to a minus b minus 1, and a minus b minus 1 expressed in the form n into some integer. Right here for some k, here don't write y, or write here for some integer y, here write y. And then we have ab is minus ny is equal to 1, and therefore greatest common divisor of a and n is 1. So right here n in bracket minus y, like this, n into minus k, and therefore greatest common divisor of a and n is 1. And in second part we assume that greatest common divisor of a and n is 1, and therefore 1 expressed as a into x plus n into y. So write either x and y notation or p and q. In this theorem, p and q are the notations. So we have again the same method. We have this, and the n bar is 0. So n into y bar is 0 bar, and therefore we have a bar into x bar is 1 bar, means a bar has inverse x bar. That is the inverse of a bar exists. The element a bar has inverse, and what is it? It is x bar. Okay. So this is the, both the theorems are same in different notation, different languages. So these examples, that what is inverse of the residue class, I bar into j bar is 1 bar, then I bar inverse is j bar, or we can say that j bar inverse is I bar. And when the inverse of element exists in multiplicative inverse exists if the greatest common divisor is 1. So in Z8 the inverses of only 4 elements exist, and what are that? 1 bar inverse is itself 1 bar, 3 bar inverse is itself 3 bar, 5 bar inverse is itself 5 bar, and 7 bar inverse. Other elements, that is 0 bar, 2 bar, 4 bar, and 6 bar does not have multiplicative inverses. And then prime residue class modulian. What is the definition? An element a bar in Z bar is called prime residue class modulian if and only if the greatest common divisor of a and n is 1. That is, inverse of a bar exists, or a bar is invertible. One and the same. That is, if a bar inverse exists, then we say that a bar is a prime residue class modulian. And the set of all prime residue class modulian is denoted by the notation Zn star. So Zn contains all residue classes, and Zn star means what? The set of prime residue classes. A bar belongs to Zn, that is the element of Zn such that the greatest common divisor of a and n is 1, means the a bar inverse exists. In a inverse of a bar exists, or a bar is invertible, then it belongs to Zn star. So for instance, what is Z8 star? Z8 is this. Z8 contains these 8 elements. But what is Z8 star? Z8 star is 1 bar, 3 bar, 5 bar, and 7 bar, because these 4 elements has multiplicative inverses. And so Z8 star is what? 1 bar, 3 bar, 5 bar, and 7 bar, contains 4 elements. In this fashion, if we write Z6 star, what is Z6 star? Z6, here is the table for Z6. Z7, okay, Z7 star is what? So Z7 is this, and Z7 star is what? 1 bar, 2 bar, 3 bar, 4 bar, 5 bar, 6 bar, because all these 1 bar, 2 bar, 3 bar, 4 bar, 5 bar, 6 bar has multiplicative inverses. So contains, Z7 contains 7 elements, and Z7 star contains 6 elements. So what are that? 1 bar, 2 bar, 3 bar, 4 bar, 5 bar, and 6 bar. So what is Zn star means what? The set of prime residue classes. And when we say the residue class is prime residue class, if its multiplicative inverse exists. So in Z8, 1 bar, 3 bar, 5 bar, and 7 bar are prime residue classes, because the inverses, multiplicative inverse of 1 bar, 3 bar, 5 bar, 7 bar exist in Z8. So find the same example, that is find all pairs in Z8 such that. Then Euler's function phi. What is the meaning of Euler's function phi? So the definition is also important. Let n belongs to n, means n is natural number. N is 1, 2, 3, 4, 5. Then phi n is the number of integers less than n and relatively prime to n. And we define phi 1 as separately 1. So this is the definition, that what is phi n is the number of integers less than n and relatively prime to n. When we say two numbers are relatively prime if their greatest common divisor is 1. Or in another form, we say that the what is phi n? Phi n is the number of residue classes, prime residue classes, number of prime residue classes modular. So this is another definition. What is the Zn star? Set of all invertible residue classes. So number of elements in Zn star is denoted by phi n. So what is phi 8? Phi 8 is 4. What is phi 8? Phi 8 is 4. So here is the another form of definition. Phi n is what? The number of integers less than n and relatively prime to n. And phi 1 is what? Is called, then phi is called Euler's phi function. Does it not function? Euler's, either write phi function or Euler's phi function. So phi n is what? Number of elements in Zn star. Is another definition. And that is Zn star is what? Set of all prime residue classes. This Z8 is set of all residue classes of module 8, and Z8 star is what? Is the set of prime residue class module 8. And so in Z8, here Z8 star is this, and so Z8 1. So phi 8 is 4. Or we can also find in by using this definition phi 8, 1, 3, 5, 7 are integers less than 8 and relatively prime to 8. So we can find phi 10. Here phi 10 is 4. Why? Because the numbers starting from n belongs to n. So we start from 1. So 0 and 10 greatest common divisor is 10. But 1 and 10 greatest common divisor is 1. 2 and 10 greatest common divisor is 2. So 2 is not prime residue class. 2 is not the number less than number relatively prime to 8, 10. So we have to find phi 10 means phi 10 is the number of integers less than n and relatively prime to n. So first find the number of integers relatively prime to n. So what are the numbers relatively prime to 10? 0 is not relatively prime to 10 because 0 and 10 greatest common divisor is not 1. And then 1 and 10 greatest common divisor is 1. Then 2 and 10 greatest common divisor is 2. 3 and 10 greatest common divisor is 1. So 3 is the relatively prime to 10. 4 and 10 are relatively prime? No, because 4 and 10 greatest common divisor is 2, not relatively prime. 4 is not relatively prime to 10. 5 is not relatively prime to 10 because 5 and 10 greatest common divisor is 5. Then 6 and 10, 6 is not relatively prime to 10 because 6 and 10 greatest common divisor is 2. Then 7 and 10, yes, 7 and 10 greatest common divisor is 1, and therefore 7 is what? Is relatively prime to 10. Then 8 and 10 greatest common divisor is 2, and so 8 is not relatively prime to 10. Then 9 and 10, yes, 9 and 10 are relatively prime because 9 and 10 greatest common divisor is 1. So these 4 numbers are what? These are the numbers less than 10 and relatively prime to 10. What are the numbers? 1, 3, 7 and 9. These are the 4 numbers, integers less than 10 and relatively prime to 10. As greatest common divisor of 1 and 10 is 1, 3 and 10 is 1, 7 and 10 is 1, 9 and 10 is 1. And therefore phi 10 is 4. Or by using another definition, find Z10 star. So what is Z10? Z10 contains 10 elements, 0 bar, 2 bar, 1 bar, 2 bar up to 9 bar, Z10. And then find prime residue classes, that is find Z10 star. So here is we can find phi 8 by using this definition. That is, what is Z8 star? This 1 bar, 3 bar, 5 bar, 7 bar. And what is Z phi 8 then? 4, because 1, 3, 5, 7, 1, 3, 5, 7 are less than 8 and relatively prime to 8. So we find the numbers less than 8 and relatively prime to 8. What are that? 0 is not relatively prime to 8. 1 is relatively prime to 8. 2 is not relatively prime to 8 because 2 and 8 greatest common divisor is not equal to 1. 3 is relatively prime to 8. 5 4 is not relatively prime to 8. 5 is relatively prime to 8. 7 is 6 is not relatively prime to 8 because 6 and 8 greatest common denominator is 2, and 7 is relatively prime. So these are the numbers, 4 numbers less than 8 and relatively around 8, and therefore phi 8 is what, 4. So we can find phi n by using two methods. Either use this definition or use this definition, that phi n is number of elements in Zn star, one and the same. Because in Zn, when a bar inverse exists, that is when a bar is prime residue class. If the a bar inverse exists, then we say the a bar is prime residue class. So when a bar is a prime residue class, if the greatest common denominator of a and n is 1, and if the greatest common denominator of a and n is 1, then we say that a is relatively prime to n. So both the definitions are same. That is phi n is what, the number of integers less than n and relatively prime to n, or phi n is number of elements in Zn star. The meaning of the both definitions are same. We find phi n by using either this definition or by using this trick, that find Zn star and then number of elements in Zn star is equal to phi n. So find phi n by using either by using definition or by using this method. So here is find phi 20, phi 36. So phi 20 is 8, phi 36 is 12. So how we can find phi 8? Phi 20 is 8. So find the number of integers less than 20 and relatively prime to 20. So list that integers. So if you list the integers, then what are that integers? 0 is not integer that relatively prime to 20. 1 is relatively prime to 20. 2 is not relatively prime to 20. 3 is relatively prime to 20. 4 is not relatively prime to 20. Then 5 is not relatively prime to 20. 6 is not relatively prime to 20. 7 is relatively prime to 20. Then 8 is not relatively prime to 20. 9 is relatively prime to 20. 10 is not relatively prime to 20. 11 is relatively prime to 20. Then 12 is not relatively prime to 20. 13 is relatively prime to 20. 14 is not relatively prime to 20. 15 is not relatively prime to 20. 16 is not relatively prime to 20. 17 is relatively prime to 20. 18 is not relatively prime to 20. 19 is relatively prime to 20. And then these numbers are in 8. These relatively prime numbers are 8 in number. 8 in number. So 8 numbers are relatively prime to 20 and less than 20. Similarly, find phi 36. Okay, or we can find phi 20 by another method. That is, write phi first Z20. Z20 is what? 0 bar, 1 bar up to 19 bar. And then find Z20 star. Okay. Find all prime residue class in Z12. That is, we have to find the Z12 star. So what is Z12 star? Is 1 bar, 5 bar, 7 bar, 11 bar. So how we can find? The greatest common denominator of 1 and 12 is 1. And so 1 bar is prime residue class. Then 2 bar is not prime residue class. 3 bar is not prime residue class. 4 bar is not prime. 5 bar is residue class, because 5 and 12 greatest common denominator is 1. In this way, 7 and 12 greatest common denominator is 1, 11 and 12. So 1 bar, 5 bar, 7 bar and 11 bar are prime residue classes because their inverse exists. And so Z12 star is what? 1 bar, 5 bar, 7 bar, 11 bar. And so if you find phi 12, then it is equal to 4. Here is phi 10 is 4 because 1, 3, 5, 1, 3, 7, 9 are integers less than 10 and relatively prime to 10. Phi 11 is what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So phi 11 is 10. Right here, 10 before comma, write 10. Phi 11 is 10 because less than 11 and relatively prime to 10. These 10 numbers are relatively prime to 11. And then question is find phi 12 plus phi 10 divided by phi 6. So phi 12, find phi 12 is 4, phi 10 is 4, phi 6 is 2, and then 8 by 2 is 4. So why phi 12 is 4? Why phi 12 is 4? Because 1, 5, 7, 11 are integers less than 12 and relatively prime to 12. Why phi 10 is 4? Because 1, 3, 7, 9 are integers less than 10 and relatively prime to 10. Why 5, 6 is 2? Only these two integers are less than 6 and relatively prime to 6. And so we have the answer 4. So the same question, that find composition table for Z6 and then write additive inverse and multiplicative inverse of each element. So additive inverse of each element exists because when additive inverse A bar plus B bar is 0 bar, then A bar and B bar are called additive inverse of each other. And the inverse of multiplicative inverse of this. So additive inverse is denoted by minus A bar. So here is the problem, that the previous question, composition table. Here is the question, that is minus 5 bar. What is minus 5 bar means? What? Additive inverse of 5 bar. So what is the additive inverse of 5 bar? 5 bar into plus what is equal to 0 bar? So 5 bar plus 5 bar in Z. This is not, this is the Z7 table. We have to draw the table of Z12, additive table of Z12. So in Z12, minus 5 bar. So 5 bar plus 7 bar is 0 bar. Because 5 bar plus 7 bar is what? Is 12 bar. And in Z12, 12 bar is 0 bar. So additive inverse of 5 bar is 7 bar in Z12. Like this, in additive inverse of 5 bar is what? Is 2 bar. So in Z7, minus 5 bar is 2 bar. But in Z12, minus 5 bar is 7 bar. So minus 5 bar is 7 bar. Why? Because additive inverse, and this is 7 bar inverse means multiplicative inverse. So minus 5 bar is 7 bar in Z12, because minus 5 bar, additive inverse of 5 bar is 7 bar. So the notation for additive inverse is what? Minus 5 bar or minus A bar. So here is the additive inverse of each element. So if we write minus 3 bar, so minus 3 bar is 3 bar, minus 4 bar is 2 bar, minus 5 bar is 1 bar. So the notation for additive inverse and the notation for multiplicative inverse. Additive inverse of each element exists in ZL, but multiplicative inverse exists if the greatest common divisor is 1. So these are some exercise. Solve all these problems. Their answers are given in this slide. Then this is another exercise on the Euler's 5 functions and some elements of Z5, Z3 and inverse. Here in that example number 10, we have to find the pairs such that their multiplication is 1 bar, means we have to find the prime residue classes. Which element satisfies x square is equal to x. Write the addition and multiplication table for Z3, Z6, Z8, Z11. Like Z6 is what? Additive table is this. This is the additive table for Z6. This is the multiplication table for Z6. It's called composition table for addition and multiplication. So we have to draw the table for Z3, Z8, Z11. So solve all these examples. In the next lecture, we will see the next topic.